Okay, then I turn off the captions. So, okay. So good afternoon, everybody, to this fourth lecture in fluid mechanics. It's still there. This caption. Stop transcribing. Okay. So good afternoon, everybody, for this fourth lecture. As usual, I would start with a short summary of what we have done last time, and then we will talk about new material. So today we will talk about the concept of a vortex. So we will talk a little bit more about what it means to have a vortex in a flow, because that's exactly one of those examples where we have a flow with what we call concentric streamlines. And then as the last bit of the exact solutions to Navier-Stokes, we will also look at the axisymmetric flows, so essentially pipe flows. So that we introduce the Hagen-Poiseuille profile that we talked about earlier already, but now we will formally derive it and compare it to channel flow. And then in the last maybe 10, 15 minutes, we will actually start with the second main part of this lecture, and that is boundary layer problems. So we will start with the first example of a boundary layer flow. Okay, but let me now start with a summary of what we did last time. So we were talking, or we started to talk about the vorticity equation, the vorticity transport equation. We kind of remembered that this is a compatibility condition to make sure that we have a computable pressure. But there was one aspect in the vorticity transport equation that we were kind of puzzled about, and that was this interesting additional term that appeared in the equation. Remember, we managed to get rid of the pressure. So the pressure term disappeared from the vorticity transport equation, but this term, omega dot nabla times u, appeared. And we said at the time, well, this is kind of a vorticity source term, which kind of produces or removes vorticity. And then we tried to understand what this term actually does, and we came up with this explanation that I have here on the screen, namely that if we look at the diagonal, I should maybe not look here, but if we look at omega 2, so for the transport equation of omega 2, we have then three terms encapsulated in this one here, and the middle one, which we to some extent can consider to be the diagonal term, corresponds to what we would call vortex stretching. And the basic idea is, if you have a flow field that has du2 dx2, so a change of the u2 velocity in the in the x2 direction, so in the same direction as the vorticity. So if we kind of would expand or stretch that vorticity component, well, then we would essentially get a positive dw2 d omega 2 d2. So that means if the velocity field is such that we would stretch a certain vorticity component, this would then show up as a vorticity stretching term. So just think of the vorticity as a material line, as a little piece in the flow domain, and if the flow field is such that it would expand that section, then we would have vorticity stretching. So that would be these diagonal terms. At the same time, if we have a flow field that corresponds to shearing motion, so in this case, if we again consider omega 2, so we have we look at the evolution of vorticity in the two direction. If the flow field is such that we have the du2 velocity changing as a function of x3, as in this case as a function of the vertical direction, so we would essentially tilt a fluid element from the vertical direction kind of sideways, we would actually create a little bit of vorticity in the two direction here on top. And this comes from the fact that we would actually do vortex tilting. So we have a vorticity element upwards, but the flow kind of pulls it to the side. So this is then the off-diagonal term, which we would call to be vortex tilting. So we have these two aspects, stretching and tilting, which are encapsulated in this term omega dot nabla times u. So and these are, as I said, these are source or sink terms if they go negative in the vorticity. So that's the first thing that we talked about. And then we started to calculate a few things. We essentially had two different flow cases that we looked at in which we used the vorticity transport equation. The first one was what we called unidirectional flows, when we said that all the velocity components are in one direction. And then we realized by using the vorticity transport equations, we end up with a Poisson equation for this velocity in this third direction, for this velocity W. So that means, for instance, for a duct flow, if you want to know the laminar flow in a duct or a star-shaped duct, and I do the example if we kind of have that's maybe not a good example, but let's do a better star, something like this, and we have the velocity kind of going through such a channel in this direction, and this duct would be kind of in this direction. Then what we need to do is we need to solve a Poisson equation in this cross section, and the forcing, so the inhomogeneity in the Poisson equation would be the imposed pressure gradient. So that's the first case. Then we looked also at the second case, which was concentric streamlines. Essentially when you have the flow turning around in one plane. And that is exactly the case of vortices or swirling motion of a flow. And what we have realized there is that the solution is composed of essentially two terms, either a term which is a constant divided by r plus a constant times r. And these would correspond to two different main features of a vortex. On the one hand, if we have the term that is proportional to r, that is a solid body rotation. So the further away you go from a center, the faster you become. And that would then also mean that because it's a solid body rotation, everything would rotate with this rotation. And on the other hand, if we have this 1/r behavior, we have something that is called an irrotational vortex. So a vortex without rotation, which essentially means that whatever is kind of swirling around would not rotate around its own axis. So in this case, indicated that this little arrow would always point upwards for a potential flow or for the irrotational case. And in this case, it would always rotate with the flow. Okay, so these were the main cases that we looked at, and then we started to look at one application last time, namely the application of these concentric streamlines in the form of a Couette flow, a Taylor-Couette flow. Remember, the Taylor-Couette flow is the flow between two concentric cylinders in which the two cylinders, they can rotate freely. And what we looked at last time was kind of a way of how to calculate the velocity inside or between those two concentric cylinders by exploiting the fact that we know that the general solution looks like this here. But then we also realized that we could actually also use, as an alternative way, we can look at the circulation, meaning that we're essentially stating that the circulation would correspond, or the difference in circulation would correspond to the vorticity times the area between those two closed lines where we calculate the circulation. And in this case of the Taylor-Couette flow, we had one surface out here and the other surface in here, and on which we both can calculate the circulation. And as as we now just said, this difference in circulation between, actually I should maybe, I realized that I make here a mistake. This should actually be maybe omega 0 here. That's much better. So, the difference between these two vorticities would then correspond to the area, so the green shaded area times the vorticity. And the vorticity, which is calculated, would be this 2 times b, as we know from essentially the calculation here. Okay, so now still the question is, how can we now use this to calculate the velocity field in the Couette flow? Well, we know now what the vorticity is. We have this expression that omega 1 minus gamma 1 minus gamma 0 needs to be the area times omega z. And I guess now we can actually start to calculate a little bit further. So we write that we have gamma 1 minus gamma 0 is the area times omega z. And that's what we had before. And of course, this, if we now start to fill in what we have seen, omega z is 2 times b. This is what we just calculated, or what we calculated last time, times the green area here. And the green area here is nothing else than the difference between, the area of the big circle minus the area of the small circle. So in this case, this would just be pi times r1 squared minus r0 squared. And of course, this would be 0 here. Okay. We know what gamma 0 and gamma 1 is. We have calculated this last time, so we can feed that in here as well. So essentially, we get then as the equation. Well, I could just do it a bit more clearly. So gamma 1 minus gamma 0 divided by pi times r1 squared minus r0 squared. That's just this divided by this is 2b. And of course, if I fill in now gamma 1 and gamma b, I get 2 pi times r1 squared omega 1 minus r0 squared omega 0 divided by pi r1 squared minus r0 squared. And of course, this is the same as 2b, which then of course means that I can directly calculate what the value of b is, and that will become r1 squared omega 1 minus r0 squared omega 0 divided by r1 squared minus r0 squared. And this now is the result for the constant b. Remember that what we're actually after is we want to know what the velocity u theta is, and this was, as we said, a divided by r plus b times r. And now with this vorticity, the circulation being the difference in circulation being the vorticity, this b is exactly the b that goes in here. So we have now seen an alternative derivation of at least one of the constants that appears in this velocity for the concentric streamlines. Of course, the other question is, how would we calculate A? Well, and of course there we still need to for A use one of the boundary conditions at the walls, which could be the boundary condition at the outer wall or the boundary condition at the inner wall. So essentially what I wanted to show you here is that this idea of having the vorticity being constant in one of those concentric streamline cases can be used to actually to calculate the difference between the circulation, which then in turn can be used to calculate or provide one condition to the velocity field. Okay, so with this, I would like to close the topic of the Taylor-Couette flow as one application for the concentric streamlines. And I would now go to a second application, which is actually quite relevant because that's now really a vortex. That's definition for or description of the vortex. And what we take here is the so-called Rankine vortex. Okay, sorry. So we will describe what is a Rankine vortex, and that actually is a important model for let's just say just for a general vortex. So if whenever you want to have a vortex in a flow field, you can take as the simplest example a Rankine vortex and essentially assume your flow field to be built up of a number of these model vortices. There are more or different types of model vortices in the literature, Lamb-Bosine vortices, and so on. I'm just discussing here in this course the Rankine vortex because it's kind of the simplest model vortex, but it has a quite easy kind of underlying idea. So it's very straightforward to understand the reasoning behind its inception. So the Rankine vortex, of course, is named after a person called Rankine, and this is William Rankine, who was working on these vortices. He had kind of the idea of the turbulent flow being composed of a number of small vortices which kind of transfer energies. So he has always been very interested in different types of vortical motions. And he lived in 1820 to 1872. And of course, Rankine is also known for the Rankine cycle when it comes to combustion engines, but also for the Rankine-Hugoniot condition. If you have ever studied compressible flows with shocks, the Rankine-Hugoniot condition gives you the speed of a shock, for instance. Anyway, so the basic idea of the Rankine vortex is that you actually do a combination of a solid body rotation and an irrotational vortex. So you would assume that a vortex or a Rankine vortex, that it has a center which rotates as a solid body, and then this goes up to a certain width, and outside it would decay as an irrotational vortex. So that means if you look at the vorticity distribution, if I just try to draw it here as a function of a radius, I would first plot the vorticity, so the omega z components, and then this is the radial component. So the vorticity would be such that it has a constant value up to a certain distance, which I can call A, and then it would drop to 0. So I have a core with a radius of A, which has vorticity, a constant vorticity, and then everything else would have 0 vorticity. And of course, that means that in this inner part, it would rotate as a solid body, and further away, so for distances larger than A, it would rotate as an irrotational vortex. So that's the basic idea of a Rankine vortex. And of course, now you can also understand there's essentially two different parameters that are relevant for the Rankine vortex. One is, of course, the value of this vorticity. So how much vorticity is it? And the other quantity is the size of the vortex core. And with these two values, a Rankine vortex is defined. So how does so this was now for the vorticity. How does the velocity look like? So if I draw that here in the same diagram with red instead, of course, inside the rotational region, I would have an increase which is linear, so it's proportional to r up to a certain point, and then outside it would essentially decay as 1 over r, something like this. So this I should try to plot it a bit better. This is really it should kind of decay. Oh yeah, it would decay like a 1 over r, something like that. So really to show you that you have a rotational part in the center, solid body rotation, and an irrotational part outside. Of course, there's certain advantages that you have with this Rankine vortex compared to, for instance, if you just had an irrotational vortex all the way. So in particular, you have no velocity singularity at r being 0. So the velocity does not increase to infinity as it would for if you continued just this irrotational part up to 0. And also at the same time, you have a well-defined value of the vorticity, which essentially is a circle with a given value of the vorticity, which you can calculate, how much it is. It's it's pi r squared or pi a squared times the vorticity. So it is actually a bounded vorticity that you have, a certain value that you can associate to that. But of course, this vorticity, now formally speaking, this omega z would be either 2 omega or 0 for r being lower than a, or 0 for r being larger than a. Now, there's a factor of 2 here that I use here. This is out of a convention. It doesn't need to be like that, but this is a convention that we use here. So we say that this value here is actually 2 omega for the vortex, because in this case the velocity u theta, which you then can calculate based on the vorticity, will then become directly omega r for r being lower than a, and omega a squared divided by r for r being larger than a. So this is now the velocity field and the vorticity field for a Rankine vortex. And now what I would like to show you is an animation or a picture of, I hope I can show you that, just an illustration of how the Rankine vortex looks like. I think now I need to stop sharing and I need to share the other window. Maybe I can just do it like this. So I guess now you should be able to see my PowerPoint slide. This here is an illustration that I took from Wikipedia that shows how a Rankine vortex would look like. So as you can see, there is certainly some inner part here that rotates like a solid body rotation, and then you have the outer part here where you clearly see that the velocity is slowly decaying further away. That's exactly, I mean, this center part here. Of course, you can the center part you can. The center part you can do a little bit more, a bit more accurately as a circle. So inside this circle, everything rotates as a solid body rotation. Further away, it just smoothly decays. So this is the illustration of a Rankine vortex. Okay. So now we know how the velocity field and how the vorticity field looks like in a vortex, or in a Rankine vortex in particular. There's one quantity we have actually not talked about. What about the pressure in a vortex? How is the pressure? And I prepared here a poll for you that you can think a little bit of yourself, how the pressure looks like. So if you think of, if you have a velocity field with a vortex in it, how big is the pressure? So is the pressure in the center of a vortex higher or lower, or maybe even constant, or the same value as the surroundings? The reason why I'm asking this question is because it's, of course, a very relevant property of a pressure of a vortex to actually, modify the pressure field. And of course, for us, it's very important to know in what way that the pressure field is modified. So I'm asking about the pressure in the center of a vortex. Is it lower? Is it higher? Or is it constant? Now I've got 23 answers. And yeah, it seems that about 80% of you say that the pressure in the vortex center is lowest. And that means in this particular case that democracy is correct. The effect that the vortex has, so the swirling motion has on the velocity field, is that the pressure inside this swirling part is lowest. Now, of course, you can think of why this is the case, and we will get back to this later on when we talk a little bit more about possible explanations. But maybe for now, you can just think of, you have a swirling motion, and so what happens if you are on a swirling motion? Well, there is, of course, a centrifugal force that tries to pull out everything from the center. And now, of course, if you translate the centrifugal force to a pressure force, you could kind of view it as something that draws out from the center. And in a way, this, of course, would lead to having a lower pressure in the center. But again, we will come back to that in more detail. For now, I think it's just important to realize, yes, there is a difference of the pressure, and it's typically like that the pressure is lowest in the center. Of course, now we can also say, well, why don't we just calculate it? Well, that's what we can do now. Let's just calculate it and see whether what I was saying was actually correct. How would we now calculate the pressure? Well, let's assume that the flow is inviscid, which we can do. We have talked about that last time, that the vortex solutions are essentially inviscid solutions, or at least they appear also in the inviscid equations, because we started from the vorticity transport equations, but we formulated them in such a direction where the viscous terms disappeared. So that means the solution for the concentric streamlines, so this A divided by R plus B times R, this is a solution both to the viscous and the inviscid equations. So that means for inviscid flows, we can use the Euler equations. We can use the Euler equations to determine the pressure. Well, how do the Euler equations look like? Well, essentially, it's like the Navier-Stokes equation, just without the viscous term. So we have du dt, which in the steady case just translate to be u times nabla times u. And this is the same as the pressure force and perhaps a gravitational force. So minus 1 over rho times the pressure gradient, so nabla p, plus the gravitational force, which I write here as a volume force G with a vector, meaning that there is a certain direction of this acceleration. Now, if I now look at this equation in the well, actually, I don't need to look at a specific direction. If I now just start to write down these different terms as what they really are for concentric streamlines. So I have the first term, so u times nabla times u. This essentially is just now for the velocity field that we have, because we only have the u theta component left. So we get u theta divided by r d theta times u theta. And this is in the direction of e theta. And if I now take the derivative of this e theta here, that will give me u theta squared divided by r times d e theta d theta. So this is if I just calculate this. And now, of course, the derivative of this unit vector, this actually is minus ER. Now, I'm not going to through the details of how to calculate this, but I assume that you have in basic geometry or basic calculus, you have looked at these derivatives of unit vectors. So that means that the acceleration term in that we have in that we have for the Euler equations just become minus u theta squared divided by r times ER. So the acceleration on concentric streamlines is a term which is in the negative ER direction. So just do a sketch here. So we have here a center, and we kind of are on a circular streamline. So we kind of go around on this circular streamline. Then we see that the acceleration is actually in the negative ER direction. So this would be in the direction of minus ER. And of course, what is that? It's u squared or u theta squared divided by r. So it increases quadratically with the velocity, and it decreases linearly with the radius. Well, this of course is nothing else than a centripetal acceleration. Centripetal acceleration. Centripetal because it is directed towards the center. So centrifugal would be out towards the outside, but centripetal goes towards the center. So we have a centripetal acceleration. So that's the first term here, like this. The second term would be the pressure gradient, and then the third one would be the gravitational acceleration. So the pressure gradient, well, again, in this case, we know that the pressure is a function of r, but it's not a function of theta, but it may be a function of z. So that means the pressure gradient would be only two components. It would be dp dr, 0, and dp dz in a coordinate system r theta z. We just know that the theta derivative of the gradient is 0 because it's homogeneous in the azimuthal direction. And then finally, the g vector. Of course, now we need to define a direction, but in this case, because we talk about concentric streamlines where we have a homogeneous distribution in the plane, it means that we have the gravity in the negative EZ direction. Yeah, so now we actually have our Euler equation, and already now, if you look at it, we can see that in the ER direction, we have in the ER direction, so the radial direction, we have a balance between u theta squared divided by r and the pressure gradient in the radial direction. And in the z direction, we have a balance and we have here in the z direction, we have a balance between the pressure gradient in the z direction and the gravitational force. So we have kind of split the two balances in the radial and in the axial direction. Okay. Now, let's start with being a little bit more concrete. Let's look at the inner part of the vortex. So if R is lower than A. Well, there we can do exactly these two directions, the projection in these two directions. We have the ER direction and we have the EZ direction. The E theta direction is 0 equals 0, so this doesn't really do much. Okay, so what do we have here? We have minus u theta squared divided by r times ER, which is the same as the pressure gradient in this direction. So that means minus 1 over rho times dp dr. This here is the balance in the ER direction, and of course now we can solve this. That gives you then that dp dr is, well, rho times, well, in this case we can replace the u theta squared with the velocity, which we have here, so omega r. So we have rho times omega squared times r. And if I integrate this once with respect to r, then we get the pressure, because that's what we're interested in at the end of the day, is rho omega squared r squared divided by 2 plus p of z. So some function of the pressure as a, or some dependence of the pressure as a function of z. The balance in the EZ direction, also right, that would be minus 1 divided by rho dp dz minus g is 0. And of course that means that, so again, I would now write the dp dz is rho times g. This I can integrate once with respect to z. So I get my pressure being minus rho g z plus some integration constant p0. And this now would be, this here is my integration constant, or I can also just call it a reference pressure. Okay, so what do we have now? We have, from this equation, we have the wall normal, or not the wall normal, the vertical dependence of the pressure, and from this equation we have the radial dependence of the pressure. The vertical dependence, that is what we would call the hydrostatic pressure. Essentially, it just means that the more fluid I have on top of each other, so the higher my column of fluid is, so the larger the weight of the fluid is, the larger my pressure, the more I'm compressed. So therefore, there is this dependence on Z. So the larger the Z becomes, the larger my pressure, my under pressure becomes, depending on the reference value. If I put everything together, so the radial and the wall normal dependence, I'll get my final expression for the pressure as a function of R and Z, which is then simply 1/2 times rho omega squared R squared minus rho GZ plus P0. This here is now my expression for the pressure in the inner part of the Rankine vortex. Now, of course, I could do the same game for calculating the pressure outside of the core region. The derivation is essentially very similar, so there is nothing really strange. I again just do the split in the ER direction and in the EZ direction, so in the radial direction and in the vertical direction. The equations are actually the same. It's just that the functional form of the velocity is slightly different. Now here the velocity u theta is different whether we're inside or outside of A, so the vertical region. So that means so in the ER direction, again, I have the same expression for dP dr, which is then rho times omega squared A to the 4 divided by R to the 3. And if I integrate that, my first, the radial dependence of the pressure is minus 1/2 rho omega squared A to the 4 divided by R squared plus a pressure as a function of Z. And the EZ is actually exactly the same as before because the velocity doesn't go in, so it's actually just the same hydrostatic pressure. So I can combine those again into one pressure as a function of R and Z, and this would then become minus 1/2 rho omega squared A to the 4 divided by R squared minus rho GZ plus some integration constant. Now this integration constant again comes from the EZ direction. But now that the point is, this integration constant cannot just be set to something. It is actually defined by the choice of the integration constant that I had earlier. So in this case, this C needs to be chosen in such a way that the pressure is actually continuous when you go from the pressure inside A to outside of A. So that means C in this way needs to be calculated such that the pressure is continuous at R being A. So this border between the rotational and the irrotational region. Now, of course, what one needs to do that to calculate it, essentially one evaluates one evaluates this term at A, and one evaluates this term at A, and then one calculates C with that. So this is an easy exercise, and the result will be, if one does it, if someone calculates that, C will become rho omega squared A squared plus P0. So that means that the pressure that I have at the outside, so P of R and Z, will simply become minus 1/2 rho omega squared A to the 4 divided by R squared minus rho GZ, and then we have the value for C now, which is rho omega squared A squared plus P0. So this now is the expression for the pressure outside of A. And of course, these are not just expressions, but we would actually like to look at them in a diagram. But now I see that it's already 4 o'clock, so we will take 15 minutes break before we actually look at these two expressions in a diagram and start to discuss what we can actually understand from them. Okay, so I will stop the recording